All right, let's look at 2017 Physics 1, question number 3. Looks like this disk is going with V naught, so it has a certain momentum. You can say linear momentum or angular momentum. And there is a rod. And to frictionless, and they stick together at distance x from the pivot. Now you want to make as much angular speed as possible. So let's see what's going on first. So there are actually like 3 steps. First, this one has momentum. You can say it has linear momentum of mv or angular momentum of mvx. Okay, this is actually came from r cross p, and r is pivot to where the disk is. P is linear momentum. Cross product means you have to multiply component perpendicular. So basically, this is your L vector, and that's your P vector of MB. And if you do cross product, you have to multiply two vector that's perpendicular. So in this case, the component of R that's perpendicular to this disk is actually this length. That's why I think they gave you this X, right? That's why it becomes this P is MB, and component of R, which is perpendicular to P, is actually X. So you get linear momentum of MBX. Now, when this guy collide, it's gonna apply force here. Obviously, this rod will also apply force there. So this force is actually applying torque on this rod, and remember, torque is R cross F again, but this L vector is actually from pivot to where point of contact. So this is what L vector is. So it's gonna apply torque. Because you apply torque, this will gain angular speed or angular momentum. Okay? The rod is. Right. Suppose the rod is much massive than the disk. To give rod as much angular speed as possible, so you still make the disk hit the rod left point of C at point of C or the right of the point C. So in this case, do you want to hit here or the right? In this case, you want to generate as much torque as possible. You should hit to the right of the C. But I think there's 2 explanations. One is you have certain angular momentum, which is mvx, right? Which is mvx, certain angular momentum there. Now this becomes momentum of the angular momentum of the system at the end, which is I omega. Remember, angular momentum in general form is I omega. It's like a mv of translational. So that'll be I of the system times omega. So if the left side was larger, if this goes up, because I of the system will be constant, omega will go up, right? So you want to create as much as angular momentum initially. So either you change mass, or you change initial speed, or you change the location of x, right? So if you hit right here, this will actually generate bigger initial momentum, so bigger final momentum, so that's bigger angular speed. Okay? So that's why you want to hit to the right of the C. Now if you look at part B, the Internet theorem finds the following equation for the post-collision angular speed of the rod in the situation. Regardless of whether this equation is correct, does it agree with your qualitative reasoning in part A? So in other words, does this equation omega have expected dependency on reason part A? So this omega, if you want to increase this omega, you want to increase this, right? So that's why you have mvx x goes on numerator. And if this I gets bigger, omega gets smaller, so that will be inverse relation, right? So actually you can write it as omega is mvx, initial momentum of the system, over I of the system. But this I need to talk about a little bit later. But I of the system actually consists of I of the rod plus I of the disk. And usually just leave it as I of the rod. I of the disk, since it's point mass, it's gonna be mr squared, but we'll see if we really need this. But for this analysis, I think this is good enough. So answer is yes. So you can say heavier mass or higher initial speed, or because they ask you reasoning in part A, so when x gets bigger, you get higher, you have bigger initial momentum, so you have to get bigger final momentum. That means you're going to increase omega. So either way you can explain. Part C, another student derived equation on post-collision. Angular speed omega. Oops. Without deriving an equation for post-collision, blah, blah, blah. How can you tell this equation is not plausible? In other words, what's not make physical sense? Well, first of all, I is on numerator, so bigger the I, bigger the omega. That doesn't make sense because I is inertia, right? So I goes up, omega goes up. That does not make sense. And remember, m disk is how will determine how much momentum initially you had. So if m disk goes up, your final omega has to goes up. So that doesn't make sense either. Okay, so m disk goes up, omega goes down. That also doesn't make sense. So you can explain like that, right? So once again, you have initial momentum, initial angular momentum becomes final angular momentum of I omega. Right, so just remember this. So once again, omega is mvx over I. Right? All right, part D. Immediately before colliding the rod, disk has rotational inertia about pivot is mx squared. Again, this is what I just explained. I of the point mass equals mr squared. But this r is perpendicular distance to the pivot, right? So here, remember this was the rod. This was the rod, and your mass coming in like this. Right? So your r. So when you hit this, your r is actually this length, okay? And that was given in our example as distance x. Actually, they wrote it somewhere here, right? That's why momentum inertia of the pivot for the point mass is mx squared. And angular momentum is mvx, which I'll let explain. To derive expression post-colliding omega, express your answer d m disk I x v naught. So I guess you have to use everything, right? So you want to say angular momentum initial equals angular momentum final. And the reason is because if I go little more explanation, that you apply force, this guy apply force, because there's R, this guy apply torque, this guy apply torque, but eventually they move together. So the disk will lose speed. In return, this rod will gain speed. Eventually they become same speed because they are moving it together. Okay, so that is the middle process. But anyway, you have initial momentum of the system equals final momentum of the system. Initial momentum of the system is momentum of the disk and momentum of the rod. But remember, rod was motionless initially. So initial momentum of the system only consists of the disk, angular momentum of the disk, which is m disk v naught x, which is given right there, equals angular momentum final, which is I omega. But this I is I of the system, okay? And this I consists of the disk and the rod itself. For I of the rod, I think we are just using capital I for I of the rod, and I of the disk we use mx squared, remember, right? So that was given here. So you have to say I plus mx squared m disk x squared omega, right? And they ask you what is omega. So omega is this divided by the whole thing, m disk v naught x over I plus m disk x squared, right? So that will be expression for omega. Part E, consider collision for which your equation in part D was derived, except now suppose the disk bounces backward of the rod instead of sticking to the rod. Is the positive collision angular speed for the rod greater or less than or equal? So basically, instead of they stick to themselves, did they stick and move together? If this guy hits and bounces off, will this guy spin faster? That's the question. And obviously this one will actually spin faster, but let's think about using a momentum case. So if I bring this again, so you have m disk v naught x initial momentum, which is same for both cases, equals your final momentum, which is I rod omega plus angular momentum of the disk itself. But first case was you're just moving together, so it's basically I of the rod omega plus I of the disk, which was mx squared omega, because they are same. That was the first part, right? So that's what this omega was. Remember, we factored I rod. But the second case is m disk, which is initial momentum, m disk vx equals I rod omega, but this time this value will be actually negative. So negative I disk with certain omega, right? So omega, or this is again linear momentum, so you can say mvx if you want to, if you just rebound backward. So if you think about, we were talking about I rod omega, this omega, right? We're talking about this omega, which is how fast the rod is spinning at the end. In this case, if you move this to the other side, this will actually go bigger, right? That's why it spins the post-angular speed of the rod. If it rebound, will be greater, okay? If I give you equivalence to linear momentum, it's like this. It's like one certain mass, small mass goes into V with a certain large mass, and they move together with B prime. But if this mass actually goes in, and when you collide, if this rebound, this large mass will have to go with higher speed. So this will go up to keep the same momentum as initial, okay? So everything starts from mv. So here you get mv equals m plus mb prime. But here you have mb equals negative mb plus large mb prime. Because of this negative part, this guy has to gain more momentum, okay? Or more speed. That's actually analogous to this scenario, right?